All right, folks, so let's pick up with memory elements. So we're going to start with a latch. A latch is our simplest memory device, and it's going to change output whenever the input changes. So the one that is shown here is an example of an SR latch. So when I say it's going to change the output whenever the input changes, well, there's going to be some propagation delay, but the propagation delay is going to be short. And you can see that this is constructed from basic logic gates. In fact, these are NAND gates, although we'll also use NOR gates later. So there's no clock signal, which is what we mean by it's being asynchronous. There's nothing to synchronize the input and the output. So if we want to make it a little more complicated, we will add a clock signal. And so when we add the clock signal, that is going to make it, instead of a latch, it's going to make it a flip-flop. So you can see that it's going to still be constructed from latches. There's a latch inside plus some stuff to enable the clock. And now the output depends on the clock as well as those inputs. And so, yeah, there's a little bit of a difference. So when I say latch, I mean the one without a clock signal. When I say flip-flop, I mean the one with a clock signal. But you might see some differences in naming conventions elsewhere. So what does it mean to use a clock? Well, when we use a clock signal, we can make it a level-based, we can use pulse-based, or we can use edge-based. So these are triggers. So a level trigger is going to always work when it is high or low. A pulse trigger is going to require 2 transitions, and an edge trigger is the one that I think of as using most often. Is going to look for a transition from low to high or high to low, a positive or negative transition in the clock signal. And so we will use these sort of transitions in order to synchronize behavior among different devices. So if you think about oscilloscope triggering, it's the same sort of idea. We would normally use an edge trigger in that case. So let's look through them. So here's an example of a level triggered. So the level triggered here, it doesn't have to be evenly spaced. It is evenly spaced in the purple case. It's not evenly spaced in the sort of reddish case there. So the upper case there, the purple one, is high enabled, and so when the clock is high, the input causes the output to change, and when the clock is low, the output doesn't change. The red case, you can see it's got that bar above the enable. That bar means not. And so because that means not, we're looking at then low as being the enable for this particular fictional device. So when the signal is low, then the input changes the output, and then when the when the clock, or the enable in this case, goes high, it stops. If we want a pulse trigger, we're looking for a rising and then a falling. And so you can see that we've got a rising and a falling and a rising and a falling. And so in this particular grouping, we got a rise and a fall, and so then we get something that happens. Same sort of thing, we might have pulses and then a longer space, and then pulses, they don't have to be the same width, they can be the length of time between them. It's unevenly spaced, it's fine, but it still triggers on a rising and then a falling. And then here's our edge triggered. We can have a low to high or a high to low, a positive or negative slope here. So in the green case, we're going from low to high. We call this a rising edge, versus the lower case there. I don't know what color that is. Is that a sort of brownish color? It's going from high to low. That'd be a falling edge. And so in either case, it's going to transition on the edge, which is a little different from the others. So you can see that in this case, if we got a clock signal and we're always transitioning on the rising edge, then we get this nice synchronous behavior that only occurs at a set frequency. So let's look at the latch, and then we can add in the clock to get our flip-flop. So here is an SR latch. Notice that this one's different than the previous one that I showed you. This one, instead of having NAND gates, has NOR gates. Same idea though. So we've got S and R as our inputs, and we've got Q and Q apostrophe there, which is the same as Q bar, which is the same not Q. So they are intended to be opposites, Q and not Q. So when we change S and R, we should see Q and not Q change in opposite ways. So here is our diagram of what's happening up here, and so you can map it out if you'd like. So when, good, I did animate this one. So when they're both 0, then Q and not Q are going to stay the same. So let's see, where do we have both 0? So we got both 0 right here. You can see that we get no change during that time. My pen always skips a little bit. No change during that time in Q and not Q. When S goes high, then Q is going to go high and Q, not Q, is going to go low. So where's an example of that? So S goes high right here. So Q goes high, not Q goes low. If we go the opposite way here, R goes high, then Q goes low. So here's R going high and S going low, and so Q goes low and not Q goes high. So notice that what we've got here is the S is going to set the value of Q to a 1, and the R is going to reset the value of Q to a 0. And if they're both 0, then we see no change, and we're in fact holding our value, and that's memory. So that's great. So right now, with just these three conditions here, we are seeing a memory effect. But what happens when we get 2 1s? Well, weird things happen. And so we're going to say that that case is not allowed. So if we wanted to work through this, certainly we could say that, let's see, if R is S is 0, then our next state of Q, notice that our next state of Q is going to be R NORed with not Q. So it's going to be a 0 NORed with not Q, our previous not Q. That's not very good Q. Let's draw that again. It's going to be NORed with our previous Q. Well, 0 NORed with our previous Q, or previous not Q, sorry, is going to be a not of not Q. And a not of not Q should be Q. So there we go. And same sort of thing, if R was 1 and S was 0, we'd say that Q star is going to be 1 NORed with not Q, which is going to be a not of 1, which is going to be 0. So you can work through this sort of thing, but if you try the case of R and S both being 1, you're going to get weirdness. So if R is S is 1, then Q, next state, Q star, is going to be 1 NORed with not Q, which is going to be 0. And Q not star is going to be 1 NORed with Q, which is going to be 0. So in this case, you can see that they're not opposites anymore. They should have been opposites, but they're not opposites. And so we're not going to allow that case at all. So we're just going to say that R and S should never both be 1. So the takeaway from this is that when they're both 0, we are holding the previous value, so we're holding memory there. We can always assert, that's set to 1. The R to reset, we can set it by asserting the S, and we're not going to allow R is equal to S is equal to 1. And that can lead to oscillation and bad things. So let's write this as a truth table that's a little different. So right now, we've got this written out as R and S are the inputs, and Q and not Q are the outputs. And so we're going to change this up, and instead, oh, I forgot to animate that. Okay, so that's the previous stuff. So now we're going to write this out as R, S, and Q as are all going to be the inputs, and Q star, which is the next state, is going to be the output. And I say output, but you understand that I mean the output in the sense of the next state, not the output in the sense of the output of an overall system. So let me just write output next state. So if this were the next state logic, it would be the output of that one block. So in this case, we now have 3 inputs. We have R, S, and the current state, and we're going to use all that to calculate the next state. And so there we go. So if we've got all of them being 0, then we know, well, if R and S are 0, then we know that we're going to hold the previous value. So if the previous value is 0, we get a 0. If the previous value is a 1, we get a 1. Hey, my stylus is low. So if we've got R and S being 0 and 1 respectively, then we know that regardless of what the current value of Q is, the next value of Q should be a 1. And if R is 1 and S is 0, then the next value should be a 0, regardless of what the current value is. So we can fill those in. And then what happens in this case down here where R and S are both 1? Well, we know that that is not allowed. We're going to put in some X's. We're not going to allow that case. So this is a truth table that uses the inputs and the current state as all the inputs, and then the output is the next state. So we're going to do a lot of these where we've got this next state truth table. So we could also draw this next state truth table out as a K-map, a Carnot map. So we've got the same sort of thing. We've got, let's see, we've got our next state logic here. Fill those in. We've got our next state logic that we can derive because we've got the R and S combinations, we got the Q combinations. Obviously, we only got 3 variables, so I'm going to end up with 1 on one side and 2 on the other side, which is why R and S are grouped and Q is separate. And so there's different ways you could group these. You could do just the 2 1s and the you could do just these 2 and these 2, but it's a little simpler if we do the full grouping as shown here with the blue and the green. And so your logic then is that the next state of Q is going to be S or Q and not R. So how could we draw this out? Well, let's draw it out one more way as a state transition diagram, and again we'll do more state transition diagrams. So let's consider this as a state transition diagram. We've got 2 states because our next state could take a value of a 0 or a 1, so there's only 2 possible outcomes here. And so we'll call them state 0 and state 1 just for naming. And so the output is going to be either a 0 or 1 for the next state. So if the S is 1 and the R is 0, and we started in state 0, then we know we need to move to state 1. Because we know that the output should be a 1 for the next state. And you can go back and look at your truth table. In fact, if you've got the notes in front of you, flip back so you can compare this. If we have S is 0 and R is 1, and we started in the output 1 case, well, we need to move back to the output 0 case. That's our reset condition. And what happens if we hold the values of S and R both 0? Well, then we should stay in the same state we were in. That's the memory case. So those are going to loop back to where they were. And what happens if we have the set and we're already in state 1, or the reset and we're already in state 0? Well, those also loop back. So there we go. We've got this state transition diagram that shows us if we've got state S0 or state S1, which correspond to next state of 0 or next state of 1, then we can transition between them based on the inputs, and some of the inputs will cause one state to transition to itself, which is memory. Notice what's missing here is that we've not included the case of R is equal to S is equal to 1, because that's not allowed. So we're not even going to draw it in. So there we go. There's our state transition diagram. There's our K-map, and our truth table for the next state logic was on the previous slide. So that's all the stuff that we need in order to describe the next state. So there's other types of latches. We could also look at a JK latch. Notice that this one looks kind of similar. It's got that block in there that's an SR latch, but now we've added to it. And we've added these extra AND gates to it. And when we add the extra AND gates to it, we get slightly different behavior. So we can have the same sort of timing diagram. We can have the same sort of next state logic. And what you're going to see is that if J and K are 0, then just like before, our next state is the same as our current state. If J is 0 and K is 1, our next state is 0. If J is 1 and K is 0, our next state is 1. And if they're both high, then it's going to toggle back and forth very quickly, which is similar to our previous case. It's not a great condition, but it's maybe a little bit better than the previous flat-out not allowed case. We can also do a K-map just like before. We can fill in exactly the same things from our next state truth table there. We can group them appropriately, and we can write out our next state combinational logic. So you know how to do that part. That shouldn't look any different. The difference from before is that we're writing out next state logic instead of an overall combinational logic from input to output. We can also do a D latch. I would say this is the one that I think of using much more frequently. Data or delay latch. You can see that There's a couple different ways to do it. There's this NAND gate versus a NOR gate implementation. But in both cases, they look very similar to an SR latch. The difference is that we're adding in this additional component here, an inverter. So we're going D and not D are going in. And in both cases, you get a truth table that looks like this. That it doesn't matter. That's the X, remember, so it doesn't matter. It doesn't matter what the current state is. The next state will be D. So we're just going to hold the value that shows up at D until our next state. So if you put in a value of 0, then your next state is going to be 0. If you put in a value of 1, your next state is going to be 1. And you're not Q star, the opposite of the next state, will be the opposite of your intended opposite there. Nothing funny going on. And so we'll use this one quite a bit because this makes a really simple way to build up our state machines. So if we want to add in some triggering, we might add in level triggering. So level triggering added to our SR latch makes an SR flip-flop. So here's our SR latch. I've drawn it in there. And we're adding to it this block here. Notice that what we're doing is we're ANDing R and S with the clock signal. So when the clock is true, 1, then everything behaves just like it was before. And when the clock is 0, well, then when you AND R and S with 0, you get zeros. And remember that if you're putting in zeros to the SR latch, then Q and not Q stay the same. There's no changes there. And so this does not allow any changes to occur when the clock is 0. So it's a real simple way to add a level triggering to an SR latch. So whenever the clock is low, the flip-flop is going to retain its previous values, previous output values. So here is our truth table. Here is our timing diagram. You can see that during this region, the clock is high and the output changes. During this region, the clock is low and the output stays constant, which is exactly what we'd expect. So our truth table, our next state, well, when the clock is high, then we've got memory, we've got a 1, we've got a 0, we've got a not allowed. And when the clock is low, then it doesn't matter what R and S are, we hold the previous value. So we can write out our combinational logic for that, and notice that we've just included our clock signal into the previous combinational logic. Can you do the same thing with a JK or a D flip-flop? Absolutely. You can add in a clock signal just the same way. You could also add in pulse triggering. I personally don't have a lot of use for this one, but I'm sure there's a case where you would need it. And so in this case, what we've got is a JK. We've got 2 stages essentially. We've got a first stage and we've got a second stage. And so what we're looking for is the first stage is going to respond to a rising edge. The second stage is going to respond to the falling edge. And so when you get the rising and the falling, then you get this, this changing. So again, personally, not a lot of use for it. Maybe you'll see a use for it. Edge triggering is something I see a lot more use of because I think of edge triggering as being a great way to deal with clock signals that are nicely timed because I want to synchronize everything to operate on a clock signal. And so I might always go off of a rising edge, for instance. So in this case, we've got, look at that, we've got 3 different SR latches all combined together. These are all the same sort of idea here. And so when we've got our 3 different SR latches all interconnected here, we end up with overall a D flip-flop. So when the input is a 0 and the clock is on a rising edge, then it doesn't matter what the previous state was, the next state is going to be a 0. When the D is high and the clock is on a rising edge, then your next state is going to be a 1. And then in this case, if the clock is either low or high but not on a rising edge, then we just hold the Q value, we just hold the previous one. So you can see that in our timing diagram. You're looking for these rising edges of the clock, and so you can see that your output is going to be aligned with those rising edges. And drawing a few more there. You can see that it's aligned there. When things happen like here between the rising edges, they're simply not captured. It's happening too fast to be captured by the clock. So you do want your clock to be reasonably quick. And then, that's a good point there. The last when there, that when something is captured, it is held until the next clock cycle, which means that you're always going to see it show up for that set length of time. So then, yeah, I didn't cover that. There you go. So Q star is always going to be D, same as before. So you can also have a toggle. A toggle is going to be, again, built on a D, and then it's just going to flip back and forth toggle when the input comes in. So you can always build these up from different combinations of the standard standard blocks here. The ones that I've got in the lab are all going to be the, I think I've all got the dual flip-flops, the 7474s. It's either that or 74-174, but I'm pretty sure I got the 7474s. So these are the standard symbols. They are all standard 7400 ICs. We're not going to use them in lab. Don't worry, you don't actually have to wire these up. We'll use them once in mechatronic systems too. So here's some examples of what you can do with them. You can debounce switches with the SRs. You can make your life easy with the Ds, relatively easy because you've only got the one input to them. Ts are good for counters. You can always build these up, and there's reasons to choose each of them. So here's an example of a D flip-flop implemented using a JK. Here's an example of a JK implemented using a D. You can go back and forth. So if you've got a particular state and next state, and you've got the inputs here, you can, for the R and the S, you can certainly come up with the appropriate inputs for the JK, you can come up with the appropriate inputs for the T and the appropriate inputs for the D. So you have an option here to convert back and forth. So like I've said before, I think that for our purposes in this class, the D is the most convenient, the most appropriate for a lot of what we're going to do. And so one thing that we're going to do with them is we're going to use edge triggering flip-flops for synchronizing. So what happens when you get asynchronous signals coming in? So for instance, you've got that lock again, and you've got somebody pressing the buttons, and you've got a really fast clock, so you can synchronize the button presses to the clock. Well, how do you do that? If you got the clock signal going, you put in a D flip-flop, now you guarantee that when they press the button, assuming your clock is fast enough, then the output will be synchronized to the clock, and then you know that all your logic is going to be synchronized to the clock, minus your propagation delay, obviously, which is really convenient, and that allows us to make a synchronous state machine. So the reason we might want to do that is if everything's synchronized to the clock, then we have fewer possibilities of error. So this is kind of like the noise margin we dealt with previously, but noise margin is at a voltage, and this is more in a time domain. So it does make sure that we have fewer errors. So I would say it's always nice to synchronize your inputs. So one clock signal, synchronize all of them, synchronize them all before they come into the logic. Don't gate your clock signal, obviously. And so all your asynchronous inputs are going to run through your synchronizers, and then your synchronized versions are then going to be sent to the various logic inputs. You don't fan out, you don't distribute your asynchronous. They all have to be synchronized before they move on. So you're running everything through your logic. Now it does create delays, but it's not huge delays. Okay, so we've got our logic, our combination logic, we've got our memory devices, and now we need to put this all together into a finite state machine. So that's going to be the next video, so we'll move on to that one.